Okay, so good afternoon, everybody. Welcome to the physics colloquium of UFABC. Today, we'll have the pleasure to have Professor Howard Haber. He is at the University of California, Santa Cruz for some time. And so from his CV, so he did his undergrad in physics and math in MIT. He did his PhD in the University of Michigan in '78. And also, so he received the Sackroy Prize in 2017, and probably he's best known for his book called The Higgs Hunter Guide, which helped to make a lot of calculations based on the Higgs and extensions, in a very detailed form. And here he will be talking about the Higgs again, and he will be talking about what happened and what lies ahead about the Higgs. So thanks for accepting the invitation, and please, it's all yours.
Okay, thank you. All right, so it's a pleasure to be able to give this colloquium. And before we start, I want to dedicate this colloquium in memory of Peter Higgs, who just passed away earlier this week. This was a news item that was posted on the CNN website, but it's been news around the world. So we mourn the loss of a great physicist. Okay, so the outline in this colloquium, I'll start, introducing the standard model of particle physics and give you a very, very brief history of the Higgs boson. Discuss briefly about before the discovery of the Higgs boson, there were quite a number of doubts whether the Higgs boson actually existed. But finally, 2012, it was discovered at CERN, and I'll discuss the current status of the Higgs boson data, and then mention its implications and prospects for future studies. So the history of fundamental particle physics throughout the 20th century is really the search for fundamental constituents of matter, probing smaller and smaller distances. This is a chart that the particle data group was making available to the community prior to the discovery of the Higgs boson, summarizing the standard model of particle physics as it was known, say in the early 2000s. And I will focus on the particles. So you can see leptons and quarks on the left, and gauge bosons on the right. Here it is blown up. Well, something is missing. You'll notice something kind of interesting in the boson sector of this slide, where you have the photon and the gluon, which are massless, but the weak bosons that mediate the weak force, the W plus, W minus, and Z, are quite heavy. So the ingredients of the standard model of particle physics is quantum field theory, which is basically a marriage of quantum mechanics and special relativity. There are particles, sometimes called matter, made up of elementary spin 1/2 fermions. These are the quarks and the leptons. And then the forces that the particles experience, electromagnetic, weak and strong, are mediated by spin 1 particles called gauge bosons. Notice that gravity is not included. Gravity is the strength of gravity is completely negligible in this discussion. Eventually, if I had a collider that could collide particles at an energy about 10 to the 17th times larger than the LHC, then the gravitational force would be relevant. But for now, we focus on this. The mathematical consistency, however, of this collection of particles and forces seemed to require that the gauge bosons had to be massless, whereas we know that the weak bosons, the W and Z, are quite heavy. Now, lurking underneath this whole structure is the concept of gauge invariance. And I'm not going to get technical in this colloquium, but in case there are any students in the audience, I'm sure you've seen the time-dependent Schrodinger equation in an external electromagnetic field. I've written out the Schrodinger equation there. And the Schrodinger equation is invariant under a set of transformations called gauge transformations, which I've written at the bottom. Now, if you were just doing electromagnetism, you would see the first two of those equations, but in quantum mechanics, there is, for instance, let psi be the wave function of the electron. Under gauge transformation, the electron field transforms, as I've shown you there, and that exponential is just a simple phase. And so that's a symmetry. In other words, you do this transformation and the Schrodinger equation remains unchanged. That's what we mean by symmetry. And this symmetry transformation, mathematically, you would say it's a U1 symmetry because the exponential of a pure phase is basically a complex number of magnitude 1. It's like a 1-by-1 unitary matrix. Now, this is just electromagnetism. When we include all the forces in the standard model, we would include the strong interaction force, the weak interaction force, and there's also a similar transformation, a gauge symmetry. It's a little more complicated than the one just for electromagnetism, but again, if you know some group theory, the transformations are SU3 cross SU2 cross U1. A little more complicated than this, but the implications of gauge symmetry are very interesting. And the first point is that mathematically consistent theories that contain self-interacting spin-1 particles, like the W boson and the gluons, they must exhibit a gauge symmetry. That's point one. The second observation is the gauge symmetry actually forbids an explicit mass term in the Lagrangian of a spin-1 gauge boson. So naively, it seems that if you had an electroweak gauge symmetry, which encompasses electromagnetism and the weak force, if this symmetry were unbroken, it would yield massless gauge bosons, the photon, the W plus, W minus, and Z0. Unfortunately, that's not what experiment reveals. The photon is massless, but the W's and the Z's are not. So it looks like we have to figure out a way to break this symmetry. There's an interesting way to break the symmetry where you maintain the symmetry of the Lagrangian, but the symmetry is not respected by the vacuum state. In that case, we say the gauge symmetry is spontaneously broken. So the question arises, how do we break the electric symmetry to explain the mass of W's and Z's? And what we learn in developing the theory is you just can't add a mass by hand to get the observed masses of the W's and the Z's. If you try to do that, that leads to mathematical inconsistencies, bad infinities, violations of unitarity and scattering, etc. But the spontaneous breaking that I mentioned just previously, where the fundamental laws respect the symmetry, but the ground state, namely the vacuum, violates the symmetry, is a mathematically consistent way of breaking the symmetry. And therefore gives a chance of developing a gauge theory of the electroweak force. Now, in order to do this, you have to, what it means for the ground state to violate the symmetry is that there's a condensation in the vacuum of weak charge. Now, if you want an analogy here, you can think of superconductors. In the superconducting ground state, you have a condensation of Cooper pairs, which are pairs of electrons. And that electron pair has non-zero charge. It actually has charge 2. And that condenses in the vacuum. And so inside of a superconductor, you actually have the spontaneous breaking of the electromagnetic gauge symmetry. And the photon actually behaves as if it's a massive particle. And so the idea was to bring this mechanism, which in the case of superconductivity was really done in the context of a non-relativistic theory. So bring this mechanism and see if it works in a relativistic quantum field theory. Now, the thing that has to condense to break the electroweak symmetry has to be a Lorentz invariant quantity, and therefore we're seeking something which is invariant under the Lorentz transformations, namely a scalar. So what mechanism can we use to try to break the electroweak symmetry? You can have weakly coupled scalar fields, strongly coupled scalar fields. You can even have strong interaction dynamics of a new type of force, new types of fermions, such that the fermions bound, like in the superconductor, into a spin zero state. And so the possible choices for electroweak condensate is maybe it's an elementary spin zero scalar that possesses a weak charge. Maybe it's a scalar bound state of known particles, like a bound state of a top quark and an anti-top quark, or a scalar bound state of unknown particles. As long as they have weak charge, if they condense in the vacuum, it would break the electroweak symmetry. So let's take the simplest, perhaps the simplest model you can imagine, which is just an elementary scalar. It has a potential energy density of V phi, and I've drawn the famous Mexican hat potential, where you see that if the value of the field, this is a complex field here, if the value of the field is 0, you're sitting not at the minimum of the scalar potential. And so if you want to minimize the potential energy, you have to give a non-zero value to phi, and that's effectively telling you that you have a condensation of non-zero scalar fields that define the vacuum. And what's interesting about this is that you can see from this picture that you can move around the bottom of the Mexican hat without changing the energy. And that excitation is called Goldstone boson. And it would be a massless particle because the energy does not change. And back in the early 1960s, after this Goldstone mechanism was discovered, it was a great puzzle because, of course, no such massless Goldstone bosons have ever been seen in the laboratory. And it wasn't at all clear that this had anything to do with the generation of mass for gauge bosons. And it was a remarkable discovery of quite a number of people, including Peter Higgs, but not only him, that if you now coupled this scalar field to the gauge bosons, that would-be Goldstone boson no longer appears as a physical particle, but instead it provides the longitudinal polarization for a massive gauge boson. And this is a mathematically consistent Lorentz invariant mechanism for generating mass for gauge bosons. I say at the bottom, it's unfairly called the Higgs mechanism because Higgs was one of many to have realized this. And just a little picture, just to remind you that massless spin 1 particles only have 2 spin directions allowed, 2 degrees of freedom, like the photon, you know, could be either left circularly polarized or right circularly polarized. From your quantum mechanics class, you know that a massive spin 1 particle has, you know, 3 possible m values, m equals +1, -1, or 0. So what the Goldstone boson is doing is it's providing that longitudinal spin component that allows you then to take a massless boson and create a massive boson. So, but what about the Higgs boson itself? And this is Peter Higgs was indeed the first one to realize that if you had a Goldstone boson generated by excitations at the bottom of the Mexican hat, there was an orthogonal direction to that, and in that orthogonal direction, it did cost you energy to move up the Mexican hat. And those excitations correspond to a new massive spin 0 particle, which we now call the Higgs boson. So just very quickly to show you, back in 1964, this was the first appearance of the Higgs boson that appeared in this paper. And actually 2 years later, Peter Higgs wrote down a very nice model, which is sort of a toy model of the model of electroweak physics. You see in the highlighted region the famous Higgs potential, the last 2 terms in equation 1. And a year later, Steve Weinberg, who had met Peter Higgs earlier that year and had interesting discussions with him, then generalized that abelian Higgs model into what is now known as the standard electroweak model. And you can see highlighted in equation 4 the Higgs potential that that Steve Weinberg employed. And so just to finish up here, you can see that the Higgs boson represents, you're still at the bottom of the Mexican hat, but it represents oscillations in the direction shown in this figure, where you move up the potential a little bit, and therefore you get a massive scalar particle, whereas the excitation along the rim of the Mexican hat just gets converted into the extra polarization state needed to give mass to the W and the Z. Now, with this picture, what you see is that the interactions of the Higgs fields with the gauge bosons, the quarks, the charged leptons, well, I've shown you that the Higgs fields gives mass to the gauge bosons, but you can also couple that scalar field to quarks and leptons. That's called the Yukawa coupling. And because, again, you're at the bottom of the Mexican hat, you discover that when you create that interaction, you end up producing, in addition, masses for the quarks and the leptons themselves, which otherwise would be massless in the standard model. And as a result, the strengths of the interaction of these particles with the Higgs boson are proportional to their corresponding masses. And the big takeaway from this is the Higgs boson therefore prefers to couple to the heaviest fundamental objects of the standard model. This would be the W's, the Z's, and the top quarks. And the next one down on the list would be the bottom quark. So all the interaction strengths of the Higgs bosons with the particles of the standard model predicted. The one thing the standard model did not predict was the actual mass of the Higgs boson. And but once you know the mass, you basically know all of its properties. Now, a little bit of a warning here. We say that the Higgs boson is the origin of mass. That's a little bit too glib. It's the origin of the masses of the gauge bosons, and it's the origin of the mass of the fundamental fermions of the standard model. But your mass does not come from the Higgs boson. Well, a very small part of it does, but most of your mass comes from the actual protons and neutrons contained in the atoms of your body. And most of the mass of the proton and the neutrons arise from the binding energy involved in constructing a proton and a neutron from the constituent quarks and gluons. So just a little aside there. I was always amused by this. Back in May 2007, a famous cartoonist for the New Yorker by the name of Ross Chass produced this interesting cartoon. And back in 2007, it was realized that the Higgs boson is a pretty elusive guy, because proposed initially in 1964 and in the context of the standard model in 1967, and yet 40 years later still had not been discovered. So given the fact that there was a long period where the Higgs boson was searched for but not found, there were doubts in the community that the Higgs boson actually existed. And one interesting part of this story goes way back to 1939, where it was realized by Weisskopf in an amazing paper that the scalar fields, or actually more generally bosonic fields, behave very differently than fermion fields. And in particular, the mass of a boson is quadratically sensitive to a very high energy scale, compared to fermions, which are only logarithmically sensitive. And so what you would expect is that if you had a theory of an elementary scalar field, then that theory must break down basically at an energy scale not too far away from the rest energy of that scalar mass. Another way to say this is that if you had to understand what the mass, actually it's just for bosons, it's the squared mass of a boson, you would expect it to be proportional to some fundamental mass scale or energy scale. And so if the standard model were correct, and the Higgs boson, which we now know has mass of 125 GeV, then you would expect that there must be some fundamental scale sitting up, which is pretty close, say in the TeV region. And in order to understand how the Higgs boson ended up getting a mass of around 125 GeV. Now, this quadratic dependence has a coefficient, and the coefficient, usually particle physicists will say, well, we expect this coefficient to be of order 1, and it could get contributions from lots of places. Now, suppose that this scale is not a TeV, but say the scale of gravity, which is sitting up at the Planck scale, which is 10 to the 19th GeV, then the only way you could understand how a Higgs boson or any of the massive gauge bosons could have masses of order 100 GeV is as if that coefficient is incredibly small. And since that coefficient gets contributions from a whole bunch of places, you would have to have a remarkable cancellation. And that seems very unnatural. And so as a result, by the way, here in that Weisskopf paper, I'm highlighting his distinction between the behavior of particles obeying Bose statistics as compared to Fermi statistics. But in any case, so theorists worried about this unnatural Higgs boson, which seemed, and the corresponding W and Z bosons, which all had masses of around 100 GeV, which seemed very light. And well, one possibility is there's just new physics lurking close by at the TeV scale, which will explain where these masses come from, or where, another way of saying it, where the scale of electroweak symmetry breaking comes from. But you can avoid this problem by saying, well, maybe the Higgs boson is not an elementary scalar, so you can create composite models of composite Higgs bosons. You can introduce new strong interactions and break the electroweak symmetry breaking that way. This was called Technicolor models. There were even Higgsless theories developed to try to explain this. Or you can invent a new symmetry which would explain why that coefficient in front of the quadratic scale is so small. If there were a symmetry reason to explain why it was maybe in first approximation 0, you might have an explanation for why the electroweak scale is as it is observed. And in fact, the supersymmetry was proposed as a new symmetry relating bosons to fermions, and fermions are only logarithmically sensitive to the ultraviolet scale. And so that would at least give you a so-called natural explanation for the value of Higgs mass. So those were doubts about the existence of the Higgs boson. Where do we stand today? As I've just shown you, you could imagine many possible dynamical models that might be responsible for electroweak symmetry breaking, but the remarkable fact is the simplest possible model, a self-interacting complex doublet of elementary scalar fields, which yields a predicted Higgs boson, seems to be consistent with all current experimental data. And by the way, I should say, when Weinberg first wrote down this model in 1967, he was just writing it as a proof of principle. He had no reason to believe that this was going to be the model of particle physics. So he was actually surprised the way things turned out. Now, having said this, there's certainly a number of profound theoretical questions that remain. I've mentioned one of them, this question of so-called naturalness. And these strongly suggest that the complete story of electroweak symmetry breaking is not yet been written, despite the discovery of the Higgs boson. Okay, so let's move on and quickly see how the Higgs boson was discovered. After the Weinberg's paper, 1967, we had prediction that if this model were realized in nature, then there should be a Higgs boson. By the end of the 1970s, the standard model was firmly established. Early 80s, discovery of the W plus W minus Z. Top quark was discovered in 1995. All that was missing then from the standard model was the Higgs boson. But we didn't know what its mass was. And so we had colliders running in the 1990s, for instance, the LEP collider at CERN, the SLC at SLAC, all looking for the Higgs boson. They did not find it. And all you could say is if the Higgs boson existed, it had to have a mass that was too large to have been produced by a collider running at that time. Back in 1976, the first serious paper on the phenomenology of the Higgs boson was written. And at the very end of the paper, there's this great paragraph, which I've reproduced here, which says that the authors apologized to experimentalists for having no idea what the mass of the Higgs boson is. And they did not want to encourage big experimental searches for the Higgs boson, but they felt that people performing experiments vulnerable to the Higgs boson should know how it may turn out. So, of course, the following decade, theorists spent a lot of time expanding on this work. And by the end of the 80s, I was one of the co-authors of the Higgs Hunter's Guide, which summarized how you should go about finding the Higgs boson at the colliders that were about to turn on in 1990, namely the LEP collider and the SLC. They ran for about 10 years. They did not find it, but the LHC started its operations at the end of the next decade, and on July 4th, 2012, the big announcement of the discovery of the Higgs boson. First time that the Physics Letters Journal had a cover that wasn't just boringly pink. They had a special cover to announce the discovery, and the community was very excited. Now, how did LHC discover the Higgs boson? Well, first you have to produce it, and then you have to detect the Higgs boson through its decays, because the Higgs boson doesn't last very long and immediately decays into lighter particles. So if you look at the production mechanism, nearly 90% of all Higgs bosons produced at the LHC, they get produced by the fusion of two gluons. In other words, the LHC is colliding two protons. Inside the protons, you find quarks and gluons. And a gluon from one of the protons and another gluon from the second proton fuse together, they can produce a Higgs. And then there are the other ways of producing it that are less probable, but actually still relevant. And I took this slide from a conference from last year because it's a nice depiction of all of the production decay mechanisms. There's a little pie chart at the bottom that shows you how the Higgs boson decays. Its dominant decay is into a pair of bottom quarks, but there are other decays. Let me first show you that since its discovery, we know the Higgs boson is about 125 GeV in mass, and therefore one can predict as a function of the energy of your collider, the total center mass energy is plotted on the horizontal. So when LHC started, they started at 7 TeV and then 8 TeV, and then run 2, by run 2, the collider was at 13 TeV. And these are very detailed theoretical calculations of the predicted cross-sections, namely the probability for producing a Higgs boson at the LHC. And in the first two major runs, of the LHC between 2012 and 2018, roughly 9 million Higgs bosons were produced, although less than 1% of these can actually be detected by the big experiments, ATLAS and CMS. The reason being is because when you produce a Higgs and it decays, the final states look like other events which have no Higgses in them, and that's called background. And so you really have to dig deep and use statistical arguments to claim that a Higgs boson has actually been produced. As far as the decay channels, here you can see that the dominant decay is into BB bar more than half the time. The interesting thing is that the Higgs boson was discovered by the last two decays shown there, gamma gamma and 4 leptons. And those are quite rare decays, but the reason they were discovered there first is because they're very clean channels. So let's look now at the current status of the Higgs boson data. Now, when LHC upped their energy from 7 and 8 TeV to 13 TeV in the center of mass, that then constituted the second run of the LHC. And of course, they had to rediscover the Higgs boson at the new energy. And here are some plots where you can see the gamma gamma and the 4 lepton channels, and the signals are very prominent. Now, on the left-hand side, you'll notice it says data minus background. So I'll show a similar plot from the CMS collaboration where you can see that there's actually plenty of background for the gamma gamma channel. But now, if you look on the left-hand side at the top, you'll see that the units are 10 to the 3. So around the Higgs boson peak, you've got about 20,000 events. But when you subtract out the background, the signal is visible. And on the right-hand side, there is some background too, but by the way, the big peak on the left-hand side of the right-hand plot is the Z boson itself decaying into 4 leptons. But the Higgs boson is pretty prominent there. But you might ask, I just told you that the Higgs boson decays into B quark pairs, bottom quarks, because that's the heaviest of the particles that are kinematically allowed in a decay of a Higgs boson. And so you should ask, since that decay is more than 50% of all Higgs boson decays, why can't we just look in that channel? And on the right, I show you a plot of the cross sections for lots of different things at the LHC. Cross section is basically the probability of production. And if you see the second line towards the top, which is labeled sigma B, that's the production cross section for a pair of B quarks that have nothing to do with Higgs bosons. They're just produced by having 2 gluons fuse into a pair of B quarks. And the Higgs cross sections are at the very bottom of this plot. And so, in fact, there are 10 to the 7th times as many B quark pairs produced in proton-proton collisions compared to B quark pairs that arise from a decaying Higgs boson. So the background is just way too large to discover the Higgs boson directly if all you've done is produce a pair of Bs in gluon-gluon scattering. Now, in fact, the decay Higgs to BB bar has actually been discovered at the LHC, but not through the gluon process, but by the VH channel. And just let me go back to remind you, the VH channel is of 4% of all the Higgs boson production channels. But the reason why the background is less is because you're producing Higgs boson in association with the W and the Z. And you see the W and the Z decay into leptons, for instance. And that tags the event and therefore begins to reduce the background compared to just producing W and Z in association with a B-quark pair. So that, again, requires, there is significant background, but you can deal with it statistically. And in 2018, Atlas and CMS announced that they had confirmed that decay. And so the particle data group, which publishes the review of particle physics every year or so, now has an entry for the Higgs boson. And you can go to that website and look it up and see all the properties that the Higgs boson has that have been measured. So I've just show you 2 pages there. And the summary of what Atlas and CMS learned about the Higgs boson from both run 1 and run 2 at the LHC, but run 2 had most of the data. Basically, 10 years after the discovery of the Higgs boson, July 2022, both Atlas and CMS published in Nature basically a summary of what they've learned about the Higgs boson. And in this figure, what you see on the vertical axis are the production modes. So they can actually separate out different production modes for the Higgs boson. And on the horizontal axis, you see different decays of the Higgs boson. And what is plotted here is the cross-section, the production cross-section times the branching ratio, in other words, the probability that the Higgs boson decays into the final state exhibited, normalized to the prediction of the standard model. So if what we were seeing in the data was a standard model Higgs boson, you should get 1 in all these cases. And you can look at this plot, and at least to within the statistical uncertainty of the measured points, it looks pretty good. This looks like a standard model Higgs boson. There are small fluctuations in a couple of these points, but statistically speaking, you can do an analysis. And at the bottom, it says the p-value for the compatibility of the measurements and the standard model prediction is 72%. CMS collaboration has a similar plot, but I'll show a different version from CMS where it uses the fact that the standard model predicts that the couplings of the Higgs bosons, the fermions, are proportional to the mass, and to the bosons are actually proportional to the square of the mass. So if you take the square root for the bosons and plot everything on the same plot, you should see a line, a straight line. And this is the data. And this is, we see a straight line, a beautiful straight line going through all of the points. And you've measured the couplings of the Higgs boson to tops and W's and Z's through the production mechanism, and to bottoms, taus, and even the muon through the decays. And they all line up. So you can now ask, we've now discovered the Higgs boson, is this the end of particle physics? I'm going to argue that it is not. And so I made a very short list here of things that the standard model does not explain. The first point is sort of a technical point. In the standard model, neutrinos are massless. In fact, they have very small masses. You can deal with this with a very slight extension, the standard model. That's the subject of another colloquium, so I'm going to just not say anything more about that now. Now, one phenomenon that's definitely cannot be explained in the standard model is dark matter, whose existence is required by astrophysics data. And in fact, there may exist a dark sector that's very weakly coupled to the standard model that's not that has not been discovered in the laboratory because it's so weakly coupled. So there is a huge experimental effort that is attempting to discover dark matter in the laboratory. We'll have to see if it reveals a positive signal at some point. But if it does, and astrophysics data strongly suggests that it's there, this is something that would require some extension of the standard model. Standard model also does not explain the observed matter-antimatter asymmetry of the universe. If matter and antimatter were there in the early universe in equal amounts, they would have annihilated. You would have left a little bit of each, but the predicted value of the amount of matter you would have would be much, much less than what we see by orders and orders of magnitude. And so that suggests that there must have been a matter-antimatter asymmetry. And so after the annihilation of the antimatter, there's matter left over. This process is called baryogenesis, or the creation of the baryons of the universe. There's a very nice theory for this, which requires CP violation, which requires certain properties of an electroweak phase transition in the early universe. But the properties required to make this work it doesn't work in the standard model. You need something more. I've also mentioned the so-called naturalness issue about understanding the origin of the mass scale of the electroweak symmetry breaking. One other interesting little tidbit is the electroweak vacuum of the standard model may not be stable. So that's worth saying something. So here's a little picture of the Higgs potential. Now, our vacuum is sitting not at zero. It's this plot, you're supposed to see the minimum of the Higgs field being slightly off from zero. And what we meant, the Higgs mass, or the square of the Higgs mass, is related to the curvature of the potential at its minimum. So we really only know the form of the potential very close to its minimum value. And so you can ask the question, suppose you plot out the potential at very large values of the Higgs field. Well, what's its shape? Does it keep on going up? In which case we would say our vacuum is stable. Maybe there's a second minimum long way away for very, very large values of the Higgs field. In that case, our vacuum would not be stable, but to get to the metastable vacuum, you'd have to tunnel through that barrier. So that tunneling probability means that the stability of our vacuum, it may be almost stable. And you can actually do a calculation within the standard model itself to plot out what this Higgs potential looks like at large values of the field. And the most recent theoretical analysis of this shows that, in fact, the Higgs potential is not absolutely stable, but it's only metastable. Luckily, the lifetime of the universe, based on where we are on this plot, is many, many orders of magnitude longer than the 14 billion years that is the age of our universe. So in one sense, you don't have to worry about the universe ending suddenly because we decay from our current Higgs minimum to the actual minimum of the potential. It's not a worry, but still this leaves one with a slightly queasy feeling. But of course, this calculation is based on assuming that the standard model is correct all the way up to the Planck scale. So if there's new physics somewhere between the energy scales we can explore at the LHC and a very, very large energy scale, the Planck scale, which is where quantum gravitational effects would begin to become important. If there was new physics there, that could certainly change this picture. Now, Higgs physics has a lot of connections to possible existence of new physics beyond the standard model. It has connections to these questions that I posed as dark matter or naturalness or baryogenesis and other issues that suggest that the standard model is not the end of the story. This is a nice figure taken from the report of the topical group on Higgs physics that was prepared for the SNOMED 2021 study, which was made as input to the U.S. Department of Energy's study of the priorities for particle physics over the next decade. So, what are the goals of the future Higgs studies? Well, I think you want to first verify the predictions of the standard model or find small deviations from standard model predictions that would suggest new physics beyond the standard model. This requires precision studies of Higgs boson properties. Right now, the summary of the ATLAS and CMS results for Higgs physics that I showed you, I'll zip back there just for a second, like that. Those show you that we've measured Higgs properties to roughly 10%. It varies from channel to channel. Some are slightly less accurate, some are slightly more accurate, but order of magnitude, about 10% measurements. We need to do better. And again, a figure from the same report shows you some of the things you can try to measure and their connections to these profound questions associated with a fundamental theory of particle physics that might go beyond the standard model. So you can see some of the things that you want to know much better. Higgs signal strength there is that cross-section times branching ratio normalized to the standard model. So they're close to 1, say within 10%, but if you increase the precision by an order of magnitude, you might begin to see deviations. So what are the prospects for future Higgs boson studies? So looking forward, we have run 3 of the LHC, which actually is in its 3rd year now. So you might ask me, why haven't I shown you any data from run 3? The answer is there hasn't been any data presented yet from run 3. Part of the problem is that run 3 has, in 2 years, has only produced about half the luminosity that run 2 produced. Part of the problem was there was an accident at the CERN collider in the summer of 2023. So they didn't get their full run last year. In this LHC plan that you see, they were hoping to collect 450 inverse femtobarns of data in the 4 years that run 3 will be in operation. But I think people probably now think, it'll be about half that. Then there'll be a shutdown to revamp the machine. increase its luminosity by a factor of 3, roughly, maybe 4. And that's called the high luminosity LHC, which will then run for at least a decade and hopefully produce another order of magnitude of data. And so the expectation is that ultimately we'll have 20 times the size of the run 2 Higgs data set by the end of the LHC run. So here are some projections for the high luminosity LHC. On the left, you see production. Cross sections on the right, you see basically the measurement of the couplings. Kappa would be 1 in the standard model. So what this is showing you is the expected uncertainty. So if you keep in mind that the current uncertainties are roughly 10%, in some channels they're more than 10%, this would be an improvement by almost an order of magnitude by the end of high Lumi LHC. Now, the Higgs boson self-coupling is an extremely important observable, which right now there's not enough data to make a definitive statement. By the end of by the end of the high luminosity LHC, you will get some significance if the Higgs boson self-coupling is as expected in the standard model. Please excuse the phone that just went off. Okay, so so by the end of high luminosity LHC, if, for instance, the kappa lambda, which is would be 1 in the standard model, you would know that it's definitely non-zero at 95% confidence level by the end of high luminosity LHC, but you'd only really get probably a 50% measurement of the coupling, which is it's certainly not a precise measurement. And so if you really want to probe the Higgs boson self-coupling, you're going to have to go beyond the LHC and go to a new collider, a different type of collider. And people are, of course, investigating what you would need to make a better measurement. All right, so the key questions for Higgs physics that will be addressed by the LHC in the next 15 years and perhaps by a new generation of colliders that will come after the LHC. The first question you want to answer is, do the Higgs boson properties deviate from those of the standard model Higgs boson? You should also ask the following question: are there additional Higgs scalars beyond the standard model Higgs boson? And I'll give you a few motivations for why you might think that that should be true. Just keep in mind that the fermions and gauge boson sectors of the standard model are not minimal at all. And so why should the Higgs sector of the standard model just have one Higgs boson and nothing else? Now, to deal with some more profound questions, we want to know whether the dynamics of electric symmetry breaking, is there some natural behavior that gives you an understanding of the scale, the energy scale, or the mass scale of Higgs bosons and the gauge bosons? Can you do this with elementary Higgs bosons? Maybe the Higgs boson is actually composite. Will there be evidence revealed for that? And the last question I want to mention briefly is Higgs bosons can have significant implications for cosmology in the early universe. So let me make a comment about the importance of the Higgs boson self-coupling. I mentioned this before, but here's a nice picture that shows you that basically we know very little about the Higgs boson, the Higgs scalar potential. We know its curvature around the minimum. That's what the mass tells us. But beyond that, we have no experimental evidence for what the shape of the potential is. And in fact, knowing the shape is very important, for instance, to understand the nature of the electroweak phase transition. Okay, now going back to that point about extended Higgs sectors, maybe there are additional scalar particles and beyond that of a single Higgs boson. Why would you consider such an option other than the fact that why not? The rest of the Standard Model is fairly non-minimal. But here are a bunch of reasons just summarized on a single transparency. Extended Higgs sectors can modify the electroweak phase transition and facilitate baryogenesis. It can enhance vacuum stability. It can provide a dark matter candidate. I'll skip the fourth one. If you're interested, you can ask me separately. And also models that attempt to explain how where the electroweak symmetry breaking scale comes from. Those models of new physics often require additional scalar Higgs states. One of the most famous examples is the minimal supersymmetric extension. The Standard Model actually requires 2 Higgs doublets. And the 2 Higgs doublet model is one of the most well-studied extended Higgs sectors. In addition to the one scalar, which would be the one observed to date with mass 125 GeV, there would be 4 additional scalars, 2 of which neutral, 2 of which are charged. And this is a very active area of the LHC experimental search program. There's a very important caveat here, is that if you consider these extended Higgs sectors, you better make sure that it predicts that one of the Higgs bosons has properties that are at least consistent with a Standard Model like Higgs boson. This is called in the literature the Higgs alignment limit. Okay, I'll just make a couple of points relevant to what I said before. Dark matter, for instance, could be one of the neutral scalar states of a 2 Higgs doublet model. This is a very special 2 Higgs doublet model called the inert doublet model, in which all the particles of the Standard Model are even under a multiplicatively conserved quantum number. And then you add a second Higgs doublet, which is odd. And because of that, the lightest odd particle is stable, because an odd particle can't decay into 2 even particles. That would violate the conserved quantum number. And so I've just shown you an example from a paper back in 2013 of finding interesting regions of the parameter space where you get exactly the right amount of dark matter suggested by astrophysics, physical data. The LHC has explored the possibility of a 2 Higgs doublet model. Here I've plotted 2 parameters in certain special cases. There are different types of 2 Higgs doublet models depending on the structure of the Yukawa couplings of the scalars to fermions. That Higgs alignment limit, which guarantees the existence of a Standard Model like Higgs boson, in these parameters corresponds to cosine beta minus alpha equals 0. So you can see that experimentally, you've ruled out large regions of the parameter space, and the ones that survive are the ones that have a small value of this cosine beta minus alpha. Now, if you were to discover deviations of Higgs couplings, you could then explore what the implications of that by considering all a large class of models that include additional Higgs scalars, for instance, and the size of the deviations would then suggest the existence of a new mass scale. So here, again, taken from the report of the topical group on Higgs physics for no mass 2021, two scenarios were considered. If you were to measure a 1% deviation from the standard model, that's blue, 0.1% deviation is red. I remind you that high luminosity LHC will not quite get to 1%. They'll get close. If you want to get to 0.1%, you have to start to consider new colliders, for instance, new lepton colliders, which allow you to make very precise measurements of Higgs boson properties. And I'll just show you one more plot before finishing up. This was a nice paper by Kanamura et al. That showed you that if you measured deviations from standard model couplings, these kappa parameters, remember, are 1 in the exact, if standard model was exactly respected. And so if you find deviations in the kappa parameters, you can begin to map out different versions of the 2Higgs doublet model. And they called this fingerprinting the non-minimal Higgs sector. So we're at the end. And so just to summarize, the discovery of the Higgs boson provides an impressive confirmation of our theoretical understanding of mass. The fundamental particle physics, however, does not end with the standard model. But the big question is the new physics beyond the standard model accessible to the LHC or to future colliders under development? We have to admit that so far no significant deviations from standard model predictions have been confirmed, although there are a few intriguing anomalies that have appeared. We'll have to see what happens to those. But just to remind you, only 5% of the data that will be collected over the lifetime of the LHC experimental program have been analyzed. There's still a lot of room for discovery of new physics at the LHC. But of course, this is a strong motivation for developing new colliders that will come after the LHC, that will give us even a larger reach in energy and or precision. So profound discoveries at the LHC and beyond may still emerge if we are patient and persistent. So that's it. Thank you very much.
Thank you, Howard. Oops. So we have time for questions. Anybody can open your mic or write in the chat. Okay, go ahead. Andre?
Oh, hi, Howard. Thanks a lot for this very nice overview. I have like a simple question. I think you didn't have time to discuss it in more detail. What are the prospects for limits on the Higgs width? And what can we gain out of it? Like if we start to probe it with larger and larger precision.
Yeah, okay. Let me see if... So in the particle data group, you'll notice it says, and I skipped this, it says full Higgs width, that's a measurement. So you might ask, how do you measure a Higgs width at the LHC? Because the LHC is measuring a cross-section times a branching ratio. And so you're not getting a direct measurement of the Higgs width from there. So one thing the LHC can do is it can measure not only the production of Higgs bosons on shell, which means you make a Higgs boson, it has a mass of 125 GeV, and then you watch it decay. But you can actually produce a virtual Higgs boson. So in those scattering processes that I showed you, and one can show that by measuring the couplings of the Higgs boson produced off shell, in other words, it's virtual, if you compare off-shell and on-shell production and decay, you can extract the width. And this has been done at the LHC. The standard model predicts about 4 MeV. So again, the number that's coming out of the LHC, which is, still pretty crude, as you can see, the error bars are large. But this is another test of the standard model. But this is an example where you really need a lepton collider to measure the Higgs width with any accuracy. And the reason being is that at a lepton collider, because of the clean environment of the collider facility, you can actually measure the cross-section and the branching ratio separately. For instance, the way you measure the cross-section is you have an E plus E minus. It fuses into a virtual Z boson, which then couples to a Z and a Higgs. And you don't even have to see the Higgs boson itself. You can just measure the Z boson that recoils against the Higgs boson and deduce the existence of Higgs boson in that event. So by that method, you've measured the cross-section alone of the Higgs boson. And so by measuring the cross-section separately from the branching ratio, you can then deduce the width. And at a lepton collider, you can make a 10 to 20% measurement, at least at the colliders that are being proposed now. Well, one of the things you want to, one motivation for measuring the width of the Higgs boson accurately is suppose that there are channels that you don't know about. For instance, an invisible channel. Suppose there was a dark sector that a dark sector can actually couple to Higgs bosons. If you can make a measurement, if you were to discover that the width is not the value predicted by the standard model, you could deduce the existence of invisible Higgs boson decays. So that's one motivation for doing that. Does that answer your question?
Yeah, thank you. So just to conclude, so we don't have high hopes of really reducing these error bars at the LHC.
Yeah, I've never seen a statement about how much better the high luminosity LHC could do. Probably can do a little bit better, but you're not going to get a 10% measurement.
Okay.
You really need the lepton colliders to significantly improve this particular measurement.
Okay, thank you.
By the way, let me just make a point that you might say, well, why don't we try to measure the width? Yeah, so you look at these peaks and you say, let's measure the width of the Higgs boson that way. Well, the width of the Higgs boson is dominated not by the intrinsic width of the Higgs boson, but by how well the experiment could measure the 4 lepton or the 2 gamma final state. So these measurements just give you you would be able to measure the width if it were greater than 1 GeV. But you can see 1 GeV is much larger than this 4 MeV, which is what the standard model is predicting. So you need these clever methods of using both on-shell and off-shell effective couplings in order to get the width at the LHC. Okay. Other questions?
Yeah, I saw one hand, maybe.
So it was mine, but how to answer my question when answered André. So it was close.
Okay, solved. Other questions? Okay. So since you're talking about new colliders, do you have some insider information on which kind or when or?
I wish I did. If I had to make a prediction, I would say probably the most likely new collider would be the one being considered at CERN, called FCC, which is it's basically a larger version of LEP, which would start at a center mass energy of 250 GeV, and maybe it could be pushed up a little bit, I don't know, to 350 GeV. You can't go beyond that because you can't afford the electricity. But they have to build a very large new tunnel going under Lake Geneva in order to make this happen. This is very expensive. CERN is certainly pushing in that direction, and we'll know more in a couple of years, I think, about whether that project is likely to proceed. I mean, right now, one could build what's called the International Linear Collider, the ILC in Japan, if Japan were willing to give the green light. But right now, it seems to be not politically feasible. People have not given up totally on that possibility. And there'll be, for instance, an international conference in Tokyo in a couple of months discussing the physics of the ILC. I can't give you any optimism as to whether that will proceed. And China has talked about also a machine similar to the one that CERN has discussed called CEPC. But it's very hard to figure out what China's intentions are. So no news there as well. Meanwhile, people are looking even beyond this and talking about the possibility of a muon collider. But there are a lot of technological challenges that have to be overcome before that becomes a realistic possibility. So,
yeah, okay. Thanks. And meanwhile, so we have a question in the chat. Gustavo is asking, what about what LHC and high luminance LHC can tell us about the CDF measurement of the W boson?
I've not seen. I've not seen any statement from LHC saying how much better they can do compared to, say, the Run 2 measurements. I mean, Atlas just published an improved measurement that they made based on Run 2 data. But one doesn't understand the discrepancy between that and the Fermilab measurement. It's definitely harder. It's a harder measurement at the LHC than it was at the P-bar-P collider, Tevatron at Fermilab. But I don't know if there's going to be any real resolution of that in the foreseeable future. Another reason to have by the way, a future electron-positron collider. And in fact, one at least the collider that's being built, that's being considered at CERN, the FCC, they talk about first doing a run at the Z and then doing a run at the WW threshold. So that would be another way of getting more information, maybe a more accurate measurement of the W mass, but that's many years beyond LHC. So.
Okay, so probably we'll have to live with that for some time.
Yes, I'm afraid so.
Okay, so any other question? Okay, so I don't see any other questions, so let's talk. Let's thank Howard again. So thanks. I'm clapping around.
My pleasure.